and I will show you the very last thing we have done so far. But let's start with the beginning. The main question in planetary sciences is basically how to form the rocky planets. We start with a material, with the composition of the protoplanetary disk, this disk of matter surrounding the newly formed sun. So we have a material which is heterogeneous, contains a lot of different elements, like you can see on this picture of a meteorite I have in my drawer in my office. So you have this material, heterogeneous, no structure. We end up with something like that, a rocky planet which has a structure, a crust, a mantle, and a core. The questions are, how do we achieve this? How long do we need to achieve this? To do that, well, we have some theories. That is a two-step model. The first one is accretion. We start forming the first solids in the solar system, and as soon as they are formed, they start to collide against each other. So at the beginning, we have a lot of collisions. We have objects, planetesimals, then they grow bigger, there are planetary embryos, and eventually we have planets. We start with objects that are about 1 to 100 kilometers. Eventually, we have a rocky planet. The thing is, bigger the objects, less collisions, but they are more and more energetic. We will see that later when we talk about the formation of the moon. So the second step is planetary scale melting. We have formation of a planetary scale magma ocean. We have heat from the collisions, and we have also heat coming from the radioactive materials, the radioactive elements, sorry. And what happens? You have migration of the elements, compounds, minerals, according to their density. They migrate within the planetary body. That's the planetary differentiation. And then eventually, we have a structured object. At the surface, we have silicates containing light chemical elements, potassium, sodium, calcium. Then, deeper, in the mantle, we have silicates containing iron, magnesium, calcium, aluminium, titanium oxides. Then we go deeper into the outer core. We have iron, nickel alloys with sulfur. And eventually, in the inner core, we have nickel and iron alloys. Elements sorted according to density. But in details, we don't really know how that happens. Do we start with small undifferentiated bodies, bodies with the composition of the primitive solar system? We accrete them, and then eventually they are differentiated. Or do we have small differentiated objects, and they are accreted? So to answer this question, we need an object, a planetary body, where the evidences of the processes that led to the differentiation were not erased. Ideally, a planetary body with no atmosphere and no plate tectonics, like the moon. And the moon is also very interesting because the geology of the moon is relatively simple. We have the crust, which is made by anorthite, 90 to 100% anorthite in the crust. And we have basalt, the black spots you see when you look at the full moon. We have also the regolith, which is the lunar soil covering the entire planet. It's the result of the constant smashing of the surface of the moon by meteorites. Relatively simple at the first look. The thing is, we don't know much about the moon. We don't have much samples. In fact, only 1,500 kilograms of rocks. From the Apollo missions, the lunar Soviet missions, the new Chinese missions, but most of it, it's meteorites. So let's have a look at the early history of the moon, how it formed, how it evolved. Well, everything started in a very chaotic way. About 4,500 to 4,400 million years. We actually don't really know. So what happened? We have a giant impact between Earth and an object the size of Mars. We have evidences of that because we have oxygen and titanium stable isotopic ratios for the moon that are similar to those we can measure on Earth. The consequences of this giant impact are extremely important because all the volatiles are gone. Sodium, lead, arsenic, nitrogen, oxygen. Gone. Very few amounts of them remain. But the refractory elements, they remain: calcium, titanium, aluminum, uranium. When you look at the chemistry of the moon compared to Earth, the moon contains more refractory elements than Earth. So after this initial formation, we have the process of planetary differentiation. Again, we don't really know when that happened, between 4,500 to 4,400 million years. What we understand is that, again, after this giant impact, we have a lot of heat accumulated. We have also the heat produced by the radioactive elements. We have formation of a global magma ocean, the lunar magma ocean, or LMO. And as soon as this lunar magma ocean formed, it started to crystallize. Can you play the little animation? So basically what happened, we start forming minerals containing magnesium and iron. And then, starting with olivine, then we have formation of pyroxene. They sink into the liquid because they are denser, and they form different layers. Can you play it again, please? So, olivine, pyroxene sinking into the liquid, forming different layers of different composition. At some point, plagioclase, anotite, starts to crystallize, but it's less dense than the remaining liquid. It floats, and it will eventually form a network of crystals that will eventually form the crust of the moon, the anorthositic crust. The point is, this LMO crystallization sequence model is not confirmed so far. It works pretty well, but we still need confirmation. Finally, the last event in the history of the moon is the basaltic volcanic activity between 4,400 and 2,000 million years. Again, we are not sure when this volcanic activity started and stopped. The thing is, so far, in the theory of the LMO crystallization sequence, the basalts are derived from source formed during the crystallization of the LMO. And crystallization of the LMO was terminated 36 million years plus minus 32 million years. Now, if we look at the basaltic volcanism on the moon, we can distinguish three main chemical groups. The low titanium basalts, they have a titanium content lower than 6%. We have several subgroups. I will just mention the low mu basalts. They have, with respect, they are derived from a source with a low uranium-238 lead-204 ratio. They are depleted in rare earth elements compared to the other basalts. We believe they are derived from a depleted mantle source. We have also the 3 billion years old basalts. I will talk about them at the very end of this talk. Basically, the low titanium basalts, they are the most abundant basalts on the moon. We have also the high titanium basalts with a titanium content higher than 6%. And with the low titanium basalts, we believe that they are derived from the early formed cumulates during the LMO crystallization. The third important group of lunar basalts are the crypt basalts. They are named that way because they contain potassium, phosphorus, rare earth elements, and uranium. They are particularly enriched in incompatible elements compared to the other lunar basalts. And we believe that they are derived from an enriched source. One interesting aspect about these basalts, we believe they are derived from a mantle source having a high mu ratio. The point is, the crypt basalts are rare. If we look at the nature of the source of these basalts, we believe that they are derived from the last liquid that crystallized during the LMO crystallization. And this source, according to the LMO crystallization sequence hypothesis, this source would be sandwiched between the crust and the mantle layers source of the low titanium and high titanium basalt. So here are the questions. What are the processes involved in the formation and the chemical evolution of the lunar mantle? Under this big question, we have two main questions from which cumulate layers are derived the different chemical groups of basalts. And within this question, we have sub-questions. How many mantle chemical components we should expect? What are the chemical compositions of these components? And then, do we expect other chemical types of basalts? And the next big question is, when the mantle components formed? That means validation of the LMO hypothesis. And within this main question, we have these two other questions. When the basaltic volcanism really started, shall we expect exhaustion of mantle components? But then, altogether, it comes to the big question. What is the age of the moon? Unfortunately, today, I'm not going to answer this question. But I can at least give you some ideas about the chemistry of the mantle. So, how to investigate the lunar volcanism? Well, we can open the toolbox of the geochemist, and we have the radiogenic isotope geochemistry. And the approach is to determine the age of the volcanism and determine initial isotopic ratios of radiogenic elements: strontium, neodymium, lead, hafnium. Because that is the way we can chemically characterize the mantle components. So we have a pretty straightforward methodological approach. We determine accurate and reliable ages for the lunar basaltic volcanism, and we determine initial isotopic ratios for the lunar basalts, like we would do for terrestrial basalts. So how do we date lunar basaltic rocks? Like on Earth, we can apply very classic methods based on the radioactive decay of an element into a daughter, namely argon-argon, rubidium, strontium, samarium, neodymium, and uranium-lead. And we apply this technique. The isoprobe, it is controlled by this kind of equation. We have the measured isotopic ratio, we have the initial isotopic ratio, the ratio that gives us the composition of the source, the parent-daughter ratio, decay constant, and age of the rock. How it works, when we have a magma, a crystallizing magma, we have different minerals forming, they have different affinity for the chemical elements, they have different rubidium-strontium ratio in the case of the rubidium-strontium technique. So they are all aligned along an horizontal line, and because these minerals form in a common magma, they have the same initial isotopic ratio. Through time, rubidium decays, so the rubidium-strontium ratio changes, as well as the strontium ratio. So we have an evolution of the isotopic composition of the different minerals along parallel lines. And when we measure the isotopic composition today, the composition of these minerals form a line, which is the isochron. And the intersect of the isochron with the y-axis, we have the initial isotopic composition. In practice, this approach is very difficult to implement because we don't have minerals containing a lot of parent elements and no daughter element. And especially for meteorites, we cannot monitor terrestrial contamination. We are talking about meteorites that were on Earth for several years, sometimes 100 or 1,000 years. They have been contaminated by terrestrial materials. That means the isochron is likely biased. And that explains why the chemical evolution of the lunar mantle is still poorly understood. We have limited constraints on the chemical characteristics of the mantle components. We have, in fact, very few radiogenic isotope data. And these data sometimes have large uncertainties back to the isochron. If the isochron is not well constrained, we have an initial ratio that is poorly constrained with a large uncertainty. Even if we determine the age with, for example, the rubidium-strontium method, and we measure the isotopic ratio of neodymium, if the age is not precise, the calculated initial isotopic ratio will be also not precise. And many investigations in the past focused only on one isotopic system. So basically, we don't have systematics using combined strontium, neodymium, lead, hafnium initial isotopic data like we have on Earth, like there's plots where you have all terrestrial basalts forming trends towards different mantle components. And then we have poor chronological constraints on the timing of the basaltic volcanism. Again, we have few data. Sometimes they have low precision. And when a sample was investigated by different isotopic methods, the results are not consistent. We have different dates for a single sample. And that is probably related to methodological and analytical issues. So to give you an example, before we started to investigate lunar basalts, from the previous studies, we had the idea that the volcanic activity was continuous between 2600 million years and 4100 million years, and then again between 4300 and 4500 million years. What you see on this diagram is dates for meteorites, and what you can see is that for a sample, we don't have consistent dates. You see, for example, this meteorite from Northwest Africa. We have one data which is significantly younger than the other ones. And this one has a huge uncertainty. That is related to analytical and methodological issues. So back to the method, back to the methodological approach. We have few minerals suitable for dating. We cannot really monitor contamination by terrestrial material. And we have analytical and methodological problems. Nothing is lost because we have established a new method based on in situ lead dating by secondary ion mass spectrometry using ion probe instruments. Okay, in details. The principle is the construction of a 7,6 lead versus 4,6 lead isochrone using in situ measurements of minerals containing lead. So this is an image of the ion probe housed by the Museum of Natural History in Stockholm. The advantages of this approach, this technique, is analysis of lead isotopes only, lateral resolution, I will explain that in a minute, and we can monitor terrestrial lead contamination. So let's start with the lateral resolution. That's the possibility of analyzing very accurately very small phases. We target phosphates because they contain radiogenic and minor amounts of initial lead. We target also potassium feldspars, they contain only initial lead, and zirconium-bearing oxides and silicates. In this backscatter electron image, you see phosphates here, potassium feldspar here. We are talking about phases that are down to 10 microns across. So the lead-lead isochrone, a little bit different from the isochrone I've shown you before. We have the 4-6 on the x-axis. We have the 7-6 ratio on the y-axis. All the phases that form from the same magma in a crystallizing basaltic liquid, they should form a line, which is the lead-lead isochrone. On the top of it, here, we have the composition, the isotopic composition of initial lead. At the intercept of the y-axis, here, we have the composition of radiogenic lead. And with this formula, we can calculate the age of the sample. The great advantage of this approach is that we can monitor terrestrial lead contamination in fact, in practice, when we analyze a sample, we don't see a nice regression. We don't see a nice line. What we see is data scattered within a triangle formed by three components: terrestrial LED, initial LED, and radiogenic LED. And it's really important to remove data that are contaminated by terrestrial LED, because contaminated data tend to produce ages that are older than the true age. So we have established a statistical protocol to remove the data that are contaminated by terrestrial LED. So we filter the data step by step until we have data that are located along the leftmost border of this triangle. We call it the leftmost isochron. That's the data that are not contaminated by terrestrial LED. And then using this data, we can calculate accurate, precise ages. So to give you few examples of investigated samples, you see on the top the entire data set, unfiltered data. And you can see for this sample, we have just only two data trending towards the composition of terrestrial LED. In this one, we see this nice trend of data towards the composition of terrestrial LED. These data are definitely contaminated by terrestrial LED. So we have to remove this data. So this one is actually an Antarctic meteorite, and they tend to be the least contaminated. So we filter the data, and then we end up with nice, well-defined isochrons. And we have actually precise data, precise ages. So now, with this new data, we can look at the previously published data and look at analytical, methodological problems, filter them, and then we can obtain a better overview of the timing of the volcanic activity, the basaltic volcanic activity on the moon. And this is what you see on this diagram. Basically, two main magmatic phases between 3950 and 3550 million years, and again between 3400 and 3100 million years. Then, now we have a better overview of the timing of the volcanic activity. We can look at radiogenic isotopes. And we can start with lead. And the best way to constrain the chemical characteristics of the mantle components using lead isotopes is to construct theoretical evolution curves. And they describe the isotopic compositions through time. This is what you see in this diagram. Again, it's a 4676 plot. And you see these curves. Each point represents an isotopic composition at a given time. So here you have the chemical isotopic evolution of an undifferentiated lunar mantle the LMO before crystallization, starting with the formation of the moon. And then we have, at some point, at 3376 million years, we have differentiation of the different sources for the different lunar basalts. These curves are controlled by this equation, where we have the 238 uranium, 204 lead ratio, mu. We have time of formation of the source, and the initial composition of this source. This is an old model. When we built it, we made assumptions. Two assumptions. The first one is the moon was formed at 4,500 million years. People do not agree about this formation of the moon at that time. The second assumption is that all the mantle sources formed at the same time. But if you remember the LMO crystallization theory, it's not entirely true. So if we don't want to make these assumptions, we are back to this equation. If we want to solve it, we need to know the composition of the source when it formed. We need the new value of the source. We need the timing of the formation of the source. That's too many unknowns to solve this equation. So what we did is to run Monte Carlo simulations. Basically, we use an algorithm. We run 100,000 calculations, and we see if we can obtain a single value, if all the calculations converge towards a single value. And that works, actually. So we calculated the mu values for two theoretical mantle sources, the sources of the crypt basalts and the sources of the source of the low mu basalts. We were able to construct these evolution curves using these Monte Carlo simulations. But what we realized is that we can actually explain the isotopic composition of the large majority of the lunar basalts by a mixing between this creep source, an enriched source, and this low mu source, a depleted mantle source. It works very well for the low titanium basalts. It's quite satisfying for the high titanium basalts, but doesn't fit as well as for the low titanium basalts. So it works for lead, but it works also for neodymium and samarium. So we can explain the low titanium basalt by a mixing between 10 to 20% creep component, 90 to 80% depleted mantle component. What does it mean? It means that through time, we bring creep material into the mantle. Remember, this creep source is supposed to be sandwiched between the crust and the other mantle layers. We believe that we have a a thermomechanical erosion of this creep layer. And one way to do that is because we have convection. So at this stage, we can already summarize a few things. The first one, I told you, we still don't know when the moon formed. Perhaps we don't have the data. Perhaps we need more data. So far, we still don't know. It's a debate. The LMO model is still valid. At least we have a better idea about the timing of the volcanic activity. Two main phases, 1400 to 3600 and between 3400 and 3100 million years. Using this data, we can use the previously published isotopic data to make sense of it. We have a new model, binary mixing between a creep-enriched mantle component and a low-mu depleted mantle component. That explains the chemical characteristics of the low titanium basalts. For the high titanium basalts, it's not as good as it is. For the low titanium basalts, we believe this mixing is the evidence of a convection process. Now, we can go a bit further. That's the last thing we have done so far. More samples we analyze, more complexity we discover. Actually, we have recently investigated these 3 billion years old basalts I mentioned at the beginning. They don't match this binary mixing model. So, what is going on with these samples? Again, what we did is try to model few characteristics of the source of these basalts using Monte Carlo simulations, using the initial isotopic, the lead initial isotopic ratios of these basalts. And we were able to get some results, and we were able to construct this evolution curve. And it starts from the curve of the depleted mantle. The source of that 3 billion years old basalt was formed from a depleted mantle source at 4260 plus minus 20 million years. That means after the crystallization of the LMO. So on the top of the LMO crystallization process, we need something else. We need another process. And that will lead to the final conclusions of this talk. The LMO model is still valid, but it's not enough to describe the chemical characteristics of some lunar basalts. We need something else. We need convection, and people have been talking about even large impacts to transform the mantle, to produce new chemical components, to produce lunar basalts. And that's it. I I thank you very much.
Thank you for a very interesting talk about the lunar basalts. And now I would like to open the discussion. So if you have any questions. If not, then Renaud, thank you very much for
Can I ask you?
yeah.
Did you try to work something with Gusev basalt as well? Gusev, iron-bearing basalt from dark side of the moon. It is sometimes very high rich in iron and magnesium, and a lot of olivine, ferrohortonolite, and other things. It is quite spectacular.
High iron basalt.
Yeah.
Hmm.
It is many people deal with this Gusev basalt, and some of this meteorite described as Gusev basalt dominated. So it is very spectacular. Yeah. And other question is, what is the kind of rock you have on the background of this presentation? It must be rapidly quenched because it is dendroidal, and this phenocryst, this is olivine.
Yes, absolutely. So basically, it's a chemical image.
Mm-hmm.
So it's an image I made with the scanning electron microscope, and that is the composition in magnesium.
Yeah.
So indeed, you're right. That's big olivine phenocryst.
Mm-hmm.
And that, I think, it's pyroxene.
Yeah.
It's a meteorite. I like it very much. It's very spectacular. I mean, look at all these features. That's.
I have from Slovakia a very similar shape of rocks. It is ferrobasalt, iron-bearing basalt, but extremely rapidly quenched like this one here. But naturally, this olivine we have not so spectacular like it. But it looks like this big olivine suffers some magmatic corrosion.
Yeah, possibly a reaction, yes. Yeah.
Yeah, excellent.
Definitely that crystallized very quickly.
Yeah, it's really rapid quenching. Yeah.
But yeah, back to your question about very high iron lunar meteorite. We are still limited with what we can find in the rock, the phases we can identify. Sometimes we cannot apply this lead technique because there is nothing to analyze.
Yeah.
So maybe that's the case for the samples. And again, they are pretty challenging samples.
Thank you.
Thank you very much.